what I will do, I will also make a list of literature, and then I send you the PDF file, and you could then put it. Okay, anyway, so it's time to start. So as usual, I make a short repetition. So I don't see anything here. Okay. Okay. So what was actually important for me, and I think that it is important for the field, is that I have shown how to map the complex graph, the Hamiltonian defined on a complex graph with short range structure where the hopping is only on the nearest neighbor. So such a graph could be a representation of the Hilbert space. And what I have shown how to, in principle, how to map such a problem onto the problem of Rosenzweig-Porter. And this is not a mathematically, not only rigorous, but also mathematically identical map. But this is a map which actually is important because to study Rosenzweig-Porter is much simpler than to study such complex networks. And the example was a random regular graph, and this random regular graph is known to have the following structure. So if I start from any side, then and make several steps, then I see the structure like a Cayley tree, like a tree. But then, so what means the structure? This means that I do not face any loops. So I go without loops, like a tree. But then, at some point, the loops appear, because it is known that on random regular graph there are only large loops, which length is proportional to the logarithm of the number of sides. And so when I go to large distance, then I eventually face the loop, and these loops make all sides equivalent, because on the tree there is a root and there are leaves, and so sides are statistically not equivalent. But because of the loops on the random regular graph, the sides are statistically equivalent, and that makes this thing a good model for numerical simulation. But anyway, so what I'm saying is that my idea is that I locally, if graph locally is a loop, is a tree without loops, then I can use exact solution for the tree, in particular for the green function between two sides. But then this green function can be computed, and it depends on the distance between the sides. So when I average it, it depends only on the distance. Of course, before averaging, it is a random number, but after averaging, it depends only on the distance. And then what I do, I replace the off-diagonal matrix element in Rosenzweig by this green function. Of course, it is random, as I said, but what is characteristic of the Rosenzweig-Porter is that these random numbers for different n and m are all independent and identically distributed. So, as I said, this G, its distribution depends on the distance between the sides n and m. But here. But what I'm saying that there are two types of sites. The type of sites before I meet a loop, and the remote sites when there are many loops. So the thing is that you either have no loop or the number of loops become very large. And this happens when the distance is of the order of the maximal distance on the graph, which is called diameter. And then what I say is that I use these small distances in order to derive statistics of this thing. But since the most of the sites are at large distances, then in this Rosenzweig-Porter, I think of these sites n and m as sites here only at large distances. But the information of small distances is encoded in the statistics of the matrix element. And since the large distances are distances which are close to diameters, then I can put in this statistics of green function the distance equal to diameter. So all these matrix elements then here will be corresponding to the same distance, and therefore they will be identically distributed. And this is Rosenzweig-Porter. And when we do this business, we will see that the Green's function on such a graph are distributed very closely to the log normal distribution. And any log normal distribution, it has the logarithm precisely minus logarithm of the typical value, where there is a maximum of this parabola, and the variance. And what is the characteristic feature of the random regular graph is that these two things are differ only by a factor of 2. And so they are rigidly connected with each other. And this has to do with the symmetry of the tree, which was discovered long ago by Taulis, Anderson, and Abu-Chakra. And so what we have to know, two things, that the distribution of the Green's functions at large distances are broad, so the logarithm is distributed as log, h is distributed log normally. And second, that this is a distribution that depends only on one parameter. And this parameter is either variance or the logarithm of the typical number. Whereas in general, there should be two parameters here. So then as an illustration, I have shown you the result of Market-Archer, which was partially published earlier in, I think, in 2021, I think, or 22, and then more results came, and to the best of my knowledge, they are unpublished. And you see the distribution of the Green's function at large distance for the graph that represents the quantum spin chain, with the Hilbert space of the quantum spin chain. And you see that the distribution is very much parabolic, I mean, this is a log of the distribution function, and it looks very much like parabolic, and this is log normal distribution. So in fact, this log normal distribution, at least qualitatively, it corresponds to many models with spin chain. And then what I did, I wanted to study the more general log normal Rosenzweig-Porter with more general log normal distribution, and this generality is encoded in the parameter p, because this is the logarithm of the typical value, and this is the variance. And as I said, for the log normal distribution that appears when I map random regular graph on Rosenzweig-Porter, this p is equal to 1, because this thing and this thing differ by a factor of 2. But in principle, this p could be anything, and this distribution is plotted here. So the Gauss has the Gauss do not have tails whatsoever, and you see that with increasing p, tails become thicker and thicker. So on this plot, Gauss corresponds to 0p. And indeed, when we simulate this ensemble with very small p, we see the results identical to the Gaussian distribution. So this tells us that actually the tails in the distribution are very important. And second is that in almost every many-body situation, these tails are present. And then you see that this distribution has two parameters. One is usual one, the parameter that gives you the value of the typical value of h. So it is present also for the Gaussian case in the same way. And then there is the second parameter that controls the thickness of the tail. And then we derived certain criteria for localization and for ergodicity. And if you take this distribution, compute these averages, and use this criteria, you will find how this gamma depends on p at the transition, at the localization transition, and at the transition from multifractal phase to ergodic. So this is simply the calculation of these moments using this thing. So doing integrals, and then you derive this expression. But what we found in addition, because of the tails, so when your distribution has thick tails, then there is a difference, a parametric difference between the typical value and the average value. So when you have some distribution without tails like Gaussian, then this thing could differ by a factor of 2, so to say, but not parametrically different. But when you have tails, then they become parametrically different. And this gives a room for the third transition. And this third transition is between ergodic and ergodic phase. So both phases have fractal dimension 1, but the fully ergodic situation is like random matrix of Wigner and Dyson, so Porter-Thomas distribution. And what I call weakly ergodic is the situation where the Porter-Thomas distribution is is violated, and the wave function looks um, generally similar to that, but there are some regions where the wave function is small. So there are some, so to say, holes. And these holes are take finite fraction of all the sides. And therefore, or the wave function takes the finite fraction. And this is not fractal, because fractal, when the wave function occupies many sides, infinite number of sides, but zero fraction. And here the fraction is finite. Therefore, fractal dimension is one, but still this phase is different from that. So I presume that that the thermalization and eigenfunction ETH is different in this phase, and in this phase it would be very interesting theoretically to characterize ETH in this case. This was not done, but I'm sure that what I propose in connection with these tails is that there is one more transition, which is the transition between this phase and that phase. And if you use this criterion for this is actually the criterion for fully ergodic phase. If there is an equality here, then there is a transition point, and this transition point can be computed, and it is equal to such a dependence on P. So so everything is pretty well analytical here, and as a result we have the phase diagram, and where there is gamma and where there is P. And so, as I said, gamma gives you strength of disorder, and T gives you the thickness of the tails. And so when T is zero, as I said, the results are similar to the Gaussian case, because there are no tails in this case. And what we know that there are three phases. So when gamma is from 0 to 1, we have a fully ergodic case like Wigner-Dyson. Then from 1 to 2, we have multifractal phase, and then we have a localized phase. So this is the case equivalent to Gaussian Rosenzweig-Porter. But then what happens as I increase the thickness of the tails, then the region of multifractal phase is shrinking. It becomes narrow, 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 until it vanishes whatsoever. And so this curve of the transition between the multifractal and localized, and the curve, the transition between the multifractal and ergodic, they merge together, and then there is only one transition. So we have a three critical point where three phases meet together. So one of them is multifractal, the other is ergodic, and the third is localized. So at this point they meet. Also, in this point, several phases meet, but what meets here is the multifractal phase, the fully ergodic phase, and the weakly ergodic phase. So if you wish, this is also a very critical point. So the phase diagram is quite complex. So as I said, what is the weakly ergodic case? How to find out that we are not in a fully ergodic, but in the weakly ergodic. So as I said, it would be very interesting to see what happens to thermalization hypothesis, eigenfunction thermalization hypothesis, but this is not known so far. And what is known is the following: when I compute the entropy, then this entropy is inversely proportional to n to q minus 1, which signals that fractal dimension is 1. But then there is a prefactor, and this prefactor for random matrix theory, it is some number which is very well known, and of course it doesn't depend on n, but it is some number that that is known. What happens in this case, that the number is different. So the number is different parametrically, and this guy could be could be much bigger than this one. When you
Vladimir, I'm confused. Isn't there something? Do you mean the IPRs with SQ, or you mean the entropies?
I mean the entropy.
Then should there not be a log of the n?
No, but I mean entropy. So it is I call okay. Sorry. So I understand. So I mean the moment, of course. I mean the moment, the moment of the wave function.
So what people call IPR.
I mean, it is not IPR because Q could be different from 2, but it is.
Okay, general.
Yeah. So sorry. So what I mean is the moment, which is the sum of R psi squared times Q and summing over R. The entropy is the logarithm of that. So exactly. I'm sorry, it is misleading, right?
And
so I have to change the notation.
Yeah. Second question: the CQRMT. I was just recently looking for these numbers, but is there somewhere published these numbers for different Q in GUE and GUE and?
No, this yeah. So you mean what? How does it depend on the ensemble of geo?
Yeah, and also the actual numbers for the random matrices. Is it published somewhere?
It is known, so I don't remember it by heart, but I can find. So of course it is known. Okay, I will find it for you. So now I don't remember exactly, but of course it is known. So yes, so thank you for noticing this. This is not an entropy. This is the momentum. Yeah, so the thing is that when this weakly ergodic phase is far from fully ergodic, so this means that when there are many holes like this, then this coefficient is much greater than that one, parametrically greater. Yeah, and so we can speak about the transition between these two. I will show you some numerics that really shows that this is a transition. So, but numerically, this thing is so far poorly studied, and as I said, ETH is interesting to see what happens, how this transition is seen in the ETH, and then to have some more evidence that this is not a crossover but the transition. Okay, at the moment I think it is a transition, but if it will eventually is a crossover, then okay. So this should be studied. But then what I want to say that where on this plot is the random regular graph. And the random regular graph corresponds to p equal 1, as I said. So the random regular graph is this line. So when I increase disorder in the random regular graph, I go from this point upwards. So what is interesting to know is that this line doesn't cross this transition. So random regular graph is always in the weakly ergodic situation. Although when I this point of endpoint, it corresponds to very weak disorder. And so eventually this is the limit of disorder going to 0. So with random regular graph, you never have a fully ergodic situation, but this weakly ergodic one is very close to fully ergodic. In particular, this coefficient then approaches this value when I go down, meaning decrease disorder. So you see this mapping also supports the result which was declared, I would say, using the sigma model, that in the random regular graph there is no multifractal phase, but there is only ergodic and localized. So this mapping that I did, it gives you that this line comes exactly through the 3 critical point. So this means that the mapping that I did is actually sensible. It makes sense, and also that this transition from ergodic case to the localized case in the case of random regular graph is not simple because it goes through the 3 critical points. So if it would be if you go, let's say, here, it would be simple, but here it is not simple because 3 phases are meeting here, and this makes the transition a complicated story. So this is what concerns the phase diagram, and then I want to say a few words about for people who are doing numerics, a few words about how to detect the transition in general. And there is one very useful measure which is called Kullback-Leibniz divergence. And it was invented by these people, but it was invented not in connection with this random wave functions, but it was connected in connection with stock market and things like fluctuations in it. Anyway, so this is a very useful measure. If we translate it on the language of random wave functions, it is a sum like this. So there is psi squared, sum over sides. This is the index of eigenvector. And so what you do under logarithm, you may put 2 neighboring eigenvectors. So with 2 neighboring energies, or you could put eigenvectors taken at random. So you take one eigenvector and you could take another one which can be corresponding to remote energy. So these 2 things, of course, you can put here mu plus k, let's say, and then you can go smoothly from this situation to that. But these are 2 extremes. So either you take 2 neighboring, or you take completely at random to to eigenvectors. And this is the result of numerics. So the simplest is the situation where p is very small. Where p is very small, this, as I said, this is equivalent to Gaussian case. And we know that in Gaussian case, we have two transitions. One is localization transition at gamma equal 2, and then the other one, the transition between multifractality and ergodic situation at gamma equal 1. And so you see what happens. If I take this measure, I see only the localization transition. I don't see a transition here. So when I cross this point, gamma equal 2, this measure start to diverge. I mean, different colors correspond to different sizes of the system. So when size increase, this guy becomes divergent. And this is the Kullback-Vladimir divergence. Why they become divergent is clear, because if you take even two neighboring eigenvectors, they will be very different in the space. So this one and this one will be in different corners of the space. And when they are in a different corners of the space, they do not overlap, and so this thing is small. Then the logarithm is big, and this is the divergence. But then, if we take so the question is why we don't see transition between the ergodic and multifractal, and we don't see this transition because the eigenfunctions or eigenvectors for eigenvectors in the multifractal phase, they are very strongly correlated despite their fractals. So the thing is that we have, let's say, one fractal, so one of these eigenvectors, and the neighboring one is most likely belonging to the same support set. Because, as I said, you have like a piece of metal, but this piece of metal is has fractal structure. Therefore, these two most probably belong to the same support set, and when they belong to the same support set, so they this thing is this thing behaves in the same way as for Wigner-Dyson, because in Wigner-Dyson we have support set the whole space, and the other wave function also the whole space. So the only difference between these is that they overlap in the same way, but here they overlap taking the entire volume, and here they overlap only in the fractal support set. And therefore, we don't see this transition whatsoever. But if we take very remote in energy states, then most probably they will belong to different support sets. And when they belong to different support sets, they do not overlap, because the fractal takes zero fraction, and the other fractal also takes zero fraction. And if they are taken at random, they do not overlap. And when they do not overlap, this logarithm is large. And so, of course, in the finite sample, they find some pieces overlapping, but in the infinite sample, they do not overlap. And so what we see that if you take this KL2, so we see the transition at 1, so the divergence starts. But then we also see the transition at 2, even though it is softer. So the slope changes. So the speed of divergence changes. So this KL2 in principle sees both transitions, but in order to see the localized transition, this is better. And in order to see the ergodic transition, this is the only one which shows it. So then this was small p, but then we can take p, let's say, 1/2. And for p equal 1/2, our criteria, our formulas for the transition point give localization transition at 2.7 and ergodic transition at 2. So when we do this thing numerically, of course, with sizes which are not very big, then what we see that there is an intersection here, which is at 2.8. So it is pretty close to 2.7. And when we study this one, we see the intersection at approximately 205, which is close to 2. So you see that you can see this shift of transition. You can numerically obtain this phase diagram that I have shown to you as a theoretical one when the size goes to infinity. So these two things indeed gives you many things. Then also what you can do, you can make a collapse of data by choosing a different instead of gamma, you choose gamma minus gamma critical times some power of the logarithm of the size, and then all these things collapse in one, and you can find the exponent of the correlation length. So it is the fact that this collapse is possible tells you that this is a transition.
Yeah, couple of questions. For me, that's very interesting. So, first of all, is this published work?
Of course.
Yeah,
in 21.
Okay, then I need to look. But so, what's in the inset of the top lot?
What?
What's in the inset on the first?
Okay.
One?
As I said, inset is a collapse of data. This one.
Yeah.
This one simply shows you that if you blow up this thing, so you will see something at 2, but very very weak. So it is simply to say that it should be it is simply blowing up in this region. So how it intersects, and so it's nothing important. Important thing is here.
And for me, it is not so clear to understand your argument why one eigenstate, which is next to another eigenstate, should have stronger overlap.
Okay. Let me.
Really
okay. Let me repeat. So, in fact, it has to do with this picture. It has to do with this picture because, as I said, there are several wave functions that share the same support set, and they all contribute to the same mini band. But if they shared more or less the same support set, then of course they overlap despite being sparse. So they are, this is, if you wish, this is a consequence that there is a mini band. But in general, if you take, let's say, psi squared of E times psi squared of E plus omega, such correlation function, which has to do with return probability, as you know. So it is essentially the Fourier transform of return probability. And for the case which is not Rosenzweig-Porter, but let's say Anderson model or power law matrices, then there is a Chalker scaling which tells you that this is 1 over omega 1 minus d2. So you see what happens. This correlation function, which is actually an overlap of two functions shifted in the energy, and this overlap decreases very slowly with increasing the distance in the energy. It decreases with a power smaller than 1. Not exponentially. It decreases with a power smaller than 1. And this is also the signature of strong overlap in the case where we have the universality of the Cantor set. So this is so this is, in my opinion, it is very powerful thing to detect transitions, and I wanted you to know about it. But not only for transition. So in principle, but there is some hierarchy of these transitions. So the transition, localization transition is best to observe. Then there is a transition between the fractal phase and ergodic phase. And as you see, one measure could be not sensitive to it, but the other measure is sensitive. But in any case, it is more difficult to detect. But then there is the third transition as we propose. And, if they exist, or I mean, if it exists or doesn't, or it is a crossover, it is not yet a consensus about that. But this is the picture of this KL2 for the case p equal 1. And the prediction of our criteria for the logarithmically normal Rosenzweig-Porter is that transition should be at 1/2. So you see, these lines are different sizes. So this is the smallest one, then bigger, 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 bigger. And of course, this is a finite size computation. What we can do, we can make a 1 over log extrapolation as we did for f of alpha. And then when you do 1 over log extrapolation, you should see, you could see that it is indeed on one line in 1 over log. And so you can do this extrapolation. And this black line is the result of this extrapolation. So if you look at any of these lines, you do not clearly see if there is a transition at 0.5 or not, because they somehow diverge, but very slowly. When you do this extrapolation, then what you see that this curve becomes almost a straight line. and this also becomes a straight line. And then you can do continuation of these two straight lines, and this continuation intersects at point 5. What does it mean? This means the following, that this 1 over log extrapolation is only is not an exact extrapolation. So apart from 1 over n 1 over log n dependence, there is other more complicated dependence. And if I would know how to extrapolate it exactly, then possibly I would get this angle. But when I do only 1 over log extrapolation, I still have some smooth curve, and therefore the question if this is a transition or it is a crossover, it is still open. In any case, it is very weak transition for which even this measure is not enough to detect it with a certainty. So this is all what I can say about this new transition. But I wanted to tell you that this playground called log normal Wigner log normal Rosenzweig-Porter, it contains 4 different phases. So it contains localized phase, it contains multifractal, it contains 2 ergodic phases, or 1 phase which crosses over from something which is remote from Wigner-Dyson to something which is Wigner-Dyson itself. Anyway, this situation about this existence of 2 ergodic phases, it is open. This is by no means a proof, because this is a smooth curve. If I would get after extrapolation an angle, I would say, yeah, here there is a singularity, and any singularity is a transition. Okay, so this I just wanted you to know. And now we come to completely different and last topic of this course of lectures. And this is the following. So far, all the random matrices that we considered were formulated so that the matrix elements were independently fluctuating random variables. So they were not correlated. So, and this is, of course, the simplest situation, but it is not the situation that is self-evident. And moreover, if we are talking about many-body localization, then we are usually talking about some Hamiltonian which is formulated in the space. So, for instance, if we have a spin Hamiltonian, so we have a real space where there is L spins, and then there is a psi tie in the real space, and then we have a random field HI acting, let's say, on spin at a psi tie. So we have therefore so many random numbers as there is the length of the system in the real space. So we have L random numbers. But if you go to the Hilbert space and have some structure like I have discussed, then here the notion of the sites is basically the bit strings, the different bit strings, and the number of sites here is let's say 2 to L if the spin is 1/2. So you see that the number of random numbers is only L, and in the Hilbert space, if I write the Hamiltonian for many body system as a matrix, so there will be some diagonal terms, then there will be off diagonal terms, but the size of this matrix is 2L times 2L. So it is much bigger than L by L. I mean, exponentially bigger. So the thing is that when I have only L random numbers, then these diagonal, for instance, matrix elements here, it will be 2 to L of diagonal elements. And this means that they are random, but they must be strongly correlated because there are only L independent random numbers. So when I studied this RRG situation, then I had the Anderson model on the graph, and the Anderson model is when all these random numbers on the diagonal, they are all independent. But in fact, for many body system, I indeed have a graph in the Hilbert space, but the number of independent random variables is the logarithm of the size of the Hilbert space, and therefore all these things must be strongly correlated as well as of diagonal matrix elements. And this makes a situation with interaction really difficult, because the thing is that, and I show you how correlation can completely change any prediction that we have with uncorrelated matrix elements. So I just want to give simple example how important are correlations. So first of all, let's consider the following. Let's consider the so-called anti-Rosenzweig-Porter, where we have a matrix with uncorrelated of diagonal elements, like in Wigner-Dyson case. But all the diagonal elements are equal to 0. So what means that they are all equal to 0? This means that they are maximally correlated, because any one is 0. So what happens then? What happens then is that n squared of diagonal matrix element always win over these diagonal matrix elements, and such matrices have properties equivalent to Wigner-Dyson, and therefore no localization is here. So this is an example that tells you that when I correlate diagonal disorder, then I always favor delocalization. So correlation in the diagonal disorder, I mean correlation which tends to make them equal. So for instance, one can consider a correlation when with some correlation radius. Here the correlation radius is infinite, but you may consider pieces which are uncorrelated, but inside the piece they are correlated. This also will make your system less localized. So the correlation in the diagonal matrix elements, they favor delocalization. But then I can ask a question. What happens if I make correlation in the off-diagonal matrix elements. So, for instance, I can do the following. So, in all the models that I considered so far, the off-diagonal matrix elements fluctuate independently. But what I can do, I can, for instance, consider them correlated along a diagonal. So they are the same along the diagonal, but not the principal diagonal. Along the diagonals at some distance from the main one. So all the off-diagonal matrix elements the same, but if I take the neighboring diagonal, it will be different and independent from this one. So I can do such step towards correlation, making the making of diagonal elements correlated along the diagonal, but uncorrelated when I go from one diagonal to the other. Or I can do the next step and I say that all the off-diagonal matrix elements are just not fluctuating, so they are totally correlated. So the thing is that this thing changed the behavior, and that's what I want to discuss. So first of all, let's consider the correlated analogs of Rosenzweig-Porter and power law matrices. So for the Rosenzweig-Porter, we have a special diagonal, and it remains as it is. But then we have the off-diagonal matrix elements, which variance is like this. Which variance is n2 minus gamma. Variance is a square, average square. What I do instead, I say that all the off-diagonal matrix elements are square root of the variance. So the scale will be the same, but no independent fluctuations. Then I can do the same for power law matrices. So I have a diagonal disorder, but instead of independently fluctuating off-diagonal matrices, I take deterministic off-diagonal elements like this. So when they fluctuated, the variance was n minus m in the power 2 alpha, because it was variance. If I take a square root, then I will have n minus m to alpha. So this is a relative of power law and random matrices, but with totally correlated off-diagonal matrix elements of the same size. So then what will happen? So the analysis of this situation, it was spread throughout many papers, in fact, but there was no unique view on what is happening. And I presume this unique view appeared in the paper that we wrote in 2019 when we took together all this situation with partial or full correlation. This paper was quite popular. This means that it was useful, although it is written in a bad way. Anyway, so what was the result? First of all, this situation appears to be an exactly soluble model. So this soluble model appeared in physics several times and in different incarnation, in different branches of the physics. But what is important that this is an exactly soluble model. Maybe it is the simplest model which resembles beta ansatz, but it is simpler than it is of the same type of exact solubility So the references are given in our paper. As I said, I will give you the list of papers to all the lectures, and then I sent you. I prepare the file with everything. But anyway, so this is an exactly solvable model, and this exact solution shows the following. So as I said, this is the relative of Rosenzweig-Porter. For Rosenzweig-Porter, we have localized phase for gamma bigger than 2. We have fully ergodic case for gamma smaller than 1. And we have a multifractal case from 1 to 2. Here, when gamma is greater than 1, we have a localized phase, the same thing. But when gamma is smaller than 1, we don't have a fractal, a usual fractal case. We have all the way for all gamma smaller than 1, we have a critical case. I tell you what means critical, and never have the ergodic case whatsoever. So you see what happens. Yeah, so this is what happens for this analog of Rosenzweig-Porter. So you see that making off-diagonal matrix elements correlated removes the ergodic case whatsoever. So this means that localization effects become stronger. Now, here the same thing. So you but here it is even stronger, because for all values of this A, you know what we had for fluctuating of diagonal elements. When A was greater than 1, then we have localization. When A was equal to 1, we have critical situation. When A was smaller than 1, we had ergodic situation. And here we have always a localized situation, except for A equals 0. A equals 0 is this case. And in this case, we may have either localized or the critical. So you see, in all this situation, making of diagonal elements correlated favors localization. So what you see is the following. Making correlated diagonal elements, you favor delocalization. Making correlated off-diagonal elements, we favor localization. This is the general statement. But then there is a surprise, because why surprise? Suppose that this A is very small, 0.1. So this means that this is a system with long-range hopping. So this means that by one single hop, I can come from one point to any remote point of this system, and the probability of that would decrease very slow with distance, because 1 over n minus m to, let's say, 0.1. So I can easily reach a remote point by one single hop. And this would be what in classical physics would happen. So in classical physics, if I can reach a remote point by one single hop, okay, I'm there. It's not what happens in quantum physics. In quantum physics, what you have to take into account, you have to take into account the amplitude of hopping between two remote sites with one hop. Then there is another possibility to hop half distance and then another half distance. Then you can hop 1/3 of the distance and make 3 hops, and so on. And then you have to add those amplitudes with their phases, and then take the the model square, and that would be the result. And the fact, I will try to somehow to prove this fact, but the fact that even at a equal very small, you have all states localized, this means that what happens is that interference of all such passes is destructive. So they kill each other because of the phases, and that of course is only possible if there is no disorder in the off-diagonal matrix elements. Because if there is a disorder, then there are signs plus and minus, and those signs means phase 2 pi and pi. And this means that the phase of these processes will be random. So when the phase is random, it is gone, and the effect of localization is gone together. So this means that the mechanism of changing the behavior where these matrix elements are deterministic, this mechanism is a destructive interference. When I make disorder in the matrix element, even small disorder, then this localization is immediately gone. So it is very fragile. Okay, so but now again, suppose you have diagonal disorder and you have deterministic off diagonal matrix elements, as I have shown, and now you add disorder to off diagonal matrix elements. What will happen? Localization will be gone. So this is a delocalization by disorder. So you know, since Anderson, our intuition tells us disorder localizes. No, disorder may delocalize, and this is the example, because everything depends what interference does. If interference is destructive, then putting disorder, I kill interference, and I'm back to delocalized situation. If interference is constructive, then the other thing. Okay. Now, let me give you a bit of not a proof, because this is actually not a simple situation. It has a history which starts, I don't know, this model of constant of diagonal matrix elements which are fully correlated. This model, I think it is 60s. And then there was the model of deterministic hopping elements with power law. It was first considered by, I think it was first considered in 89 by Burin and co-workers. But all those was just single works. So some people knew about it, but there was no vision that correlation may do both things. So correlation in the diagonal elements favor localization, correlations favor delocalization. Correlation in the off-diagonal matrix elements favor localization. And a bit of theory, but only a bit, because this, in fact, is a big area. So now let's consider this model. let's consider this model, and let us at the moment consider it with a smaller than 1. So if it would be uncorrelated of diagonal elements of the same size, of the same typical size, then for a smaller than 1, I would have delocalized case. But when they are correlated, so what happens? So when the off-diagonal matrix elements are a power of the distance from the diagonal, or from n minus m, and they are deterministic. So first, what one can do to forget about disorder, diagonal disorder, and compute the spectrum. And this spectrum is computed just by Fourier transform, because if you have a Hamiltonian which depends on n minus m, then what you have to do, you have to make a Fourier transform, so to come to the momentum space, and then things are simple. So the spectrum, you can do this exercise, and then what you obtain for a smaller than 1, that the spectrum is like this. So the spectrum has some limit, a lower bound, and it has a divergency when a is smaller than 1. So the spectrum is dragged towards big value. In principle, all the things depend on the sign of this lambda. So when this lambda is positive, then it is like that. When it is negative, then everything changes the sign. So I consider physics is unchanged, but the spectrum, what was the lower bound becomes the upper bound, and so on. So what is important is that the spectrum here, as I said, it is a power which is not integer one, but here close to momentum pi, it is quadratic. Now, so important is that the spectrum diverges from one side. Now, now I think it will be very difficult to digest this thing, because it needs more time. But the idea of what I am going to show you is the following: that you can represent your Schrödinger equation, your problem of spectrum and wave functions, in such a way that there is a certain duality. So you can represent it. This is the initial problem, and then you can rewrite it exactly. So in some more tedious expression, but important thing is that this J, there was H and M, and this H and M was so this must be H. So this H and M was just it can be expanded in the momentum, and this is the spectrum that I have shown to you. So this is this H and M, so not J, H and M. So it has expansion in the momentum and in the momentum space, off-diagonal matrix elements become diagonal. So this spectrum, so when you do Fourier transform, off-diagonal matrix elements in the real space become diagonal matrix elements in the momentum space, and vice versa. And this is this diagonal matrix elements in the momentum space. But when I rewrite it in such a bit complicated way, I instead of H and M, I have some other hopping term, which is expressed in terms of some matrix, which also depends on NMM. And the idea, the whole idea of this manipulation is that this matrix, which essentially plays a role of H, despite of these complications, this matrix, when I represent it in terms of the momentum space, it will have the spectrum not in the numerator, but in the denominator. But so this is an exact transformation. Now, here appears some mysterious quantity E naught. This E naught can be anything, but it is important that it is beyond the spectrum. So it doesn't cross the spectrum. This is only possible if the spectrum is bounded, at least from one side. If it is bounded from below, so this E naught could be here. Now, then suppose we have chosen this E naught and it is fixed. In this case, I can do it, that it is beyond the spectrum. But the spectrum itself is divergent. So this thing here becomes arbitrarily large. And when it becomes arbitrarily large, it can be bigger than E naught. So when it is bigger than E naught, I can forget about this one. And what then happens is that this E naught will be in the denominator, and spectrum will be in the denominator, and E naught will be in the numerator when I forget this one. And then this is the whole thing, that you need two things. First, that the spectrum is bounded from at least one side. And the second thing is that in the other side, this spectrum is infinitely stretched. So you have exactly the spectrum like this, that it is bounded, let's say, from below and stretched to infinity here. And then you can do this transformation. So then, you see, then the statement is that the system with hopping like this, initial one, and the system with hopping, which is expressed like 1 over EP, they have to be to lead to the same physics, because this is an exact transformation. So if you have a situation like that, then this duality can be proven, and this means that if you have hopping which is represented in such a way, then the physics is the same if the hopping is represented by 1 over UP. This is the duality. And then, so I understand that I gave only some idea. I did not prove this transformation. It is elementary, but anyway, so one has to understand what is the condition. The condition is that the spectrum is bounded from one side, and from the other side it is infinitely stretched. Then, as I said, then I have an equivalence of physics with hopping like this and with hopping like that. But what does it mean? It means the following, that if the hopping is like this, then the spectrum, as I said, is in terms of momentum, it is given by this expression. But if the hopping matrix element is like this, then the spectrum is given by this expression. And let me represent this in the same form as this, introducing some different A. It's very simple. So if you compare this and that, you find that this dual A is 2 minus A. But because physics is the same, then there is a duality. So if I change, if I have A and I have 2 minus A, I have the same physics. But suppose that initially I have A greater than 1. Then situation is simple, because if A is greater than 1, there is a criterion of localization which is called locator expansion. So what you do, you have a sum of the diagonal matrix element and the difference in the diagonal matrix elements. And if this sum is convergent, then we have localization, because then we have a finite number of resonances, because this is the condition of the resonance. If this thing convergence, we have a finite number of resonances and localization. But convergence from mathematics, we know that suppose we have a series. Suppose we have a series like, let's say, 1 over n factorial x to n. So this series is absolutely convergent. So I can put here absolute value and it will be convergent. But suppose I have a different series, like 1 over n minus 1 to n xn. So if I take the absolute value, it will be divergent as a harmonic series. But this series is convergent. Why it is convergent? Because I can combine two terms, neighboring terms, and there is 1 minus n by minus n plus 1 because of this minus. And I have n plus 1 and here unity. So if I combine neighboring terms here together, taking into account this sign, then the resulting series will decrease like 1 over n squared, and it is convergent. But it is not absolutely convergent, because if I take the absolute value, it will be divergent. So what happens here is the following. So when A is greater than 1, then this thing is n minus m to A, which is greater than 1. Then this thing is of the order of disorder W, and it is convergent. It is absolutely convergent. So when a is greater than 1, then there's no doubt that there will be localization, independently of whether this is deterministic or it is not. But if a is smaller than 1, then of course this series is absolutely not convergent. So if I, because when I take the absolute value, this will be divergent series. But this doesn't mean that localization is not there, because for localization you have to study the series without the absolute value. You have to take into account phases, the same phases that I was talking about. And then the series may become convergent. And this is exactly what happens. So if you have a greater than 1, then you know that your series is absolutely convergent, then you have localization. But because of duality, because we have proven in this, I would say, sophisticated, I mean, it is not sophisticated, but it is like, like you have to invent this transformation from one to the other. And from this transformation, it follows that the physics at A is the same as the physics at 2 minus A. But if A is greater than 1, 2 minus A is smaller than 1. And this means that even if A is smaller than 1, we have localization. But this localization appears only because of the phases. And I told you, so there is one long hop, 2 shorter, 3 hops, and phases are important. And now, again, numerics. So this is the following. This is the logarithm of the wave function counted from the center of localization. So this is n naught is center of localization. So this is logarithm of n minus n naught, and this is the logarithm of wave function. And you see that for A is 1/2 and A is 3/2, they are parallel in log-log coordinates. So this means that it is a power law localization when each wave function falls down as a power law, but the power law is the same for 0.5 and for 1.5. But then even more drastic example. Let's take A 1.9. We have again power law localization with this power. And now take A 0.1, which is almost 0, and you have the same. But if you take 0, then the situation will be different. So there is a great difference between 0 and 0.1. And the reason is the following. The reason is the following. Everything is encoded in this spectrum. So when we have 0.1, then the spectrum is still divergent, very slowly, but it is divergent. When we have 0, then Fourier transform of constant is delta function. So if you have any power, you have a branch cut. If you have power 0, you have a delta function. And with delta function, you cannot do all these manipulations that I did. So then what you can do, you can ask a question. Okay, we have power law localization. What will be the f of alpha? And f of alpha appears to be linear with coefficients smaller than 1/2. And such f of alpha happens, I mean, this is for for this power law hopping. But this f of alpha, it happens for the Cayley tree, for the random regular graph in the localized phase. And this k is smaller than 1/2. And here, this picture shows this duality that as localization becomes stronger, this coefficient goes down. But it also goes down for a smaller than 1. So there is this duality. Now the power of power law localization, the same thing. So when you increase A, then localization gets stronger and the power increases. So it falls down more quickly. As you go to other side, it also increases. So this is amazing. So the thing is that when I faced this situation, the story was the following. I was sitting in Paris for some while, and then a guy comes to me and says, "Well, so they knew that I'm dealing things like that, and they said, well, we have a lot of numerics. We don't know how to organize it." Okay, so I'm willing to help. So I took this numerics. And there was the full hell of everything. It is even now not fully published. But then I looked at one dimension and I spotted this fantastic duality there. So I was absolutely surprised because, and all this picture of the proof of this duality, then the reason of why for A smaller than 1, I can tell you even more. There was a paper, I think some 5 years before I was involved in that. And in this paper, it was the paper by Eugene Bogomolny, who is in fact a math physicist. And he discovered absolutely correctly that when A is equal to -1, so this means that it is not falling, it is growing, there was localization. But the thing is that mathematicians somehow cannot be surprised. I was surprised enormously. And the result is this business. So this is all. Thank you for attention.
Thank you.
Okay, what I will do, I will take some time and